All right, we're taking a look at chapter 6. This title is crazy long. We are looking in chapter 6 at differential equations, which I think many of you, not all, but many of you have to take differential equations, right? Okay, so this is sort of the prior knowledge kind of information that leads into that course. And so you're going to get a little bit of a taste of that in these 4 sections in chapter 6. So to start with, I'd like to talk about just what is a differential equation. So a differential equation is an equation involving x, y, and y prime. It could also include y double prime. It doesn't have to, but it could, okay? But it has to at least have x, y, and a derivative version. A solution of the differential equations is a function that satisfies the differential equation. So in algebra, somewhere along the way, in high school, undoubtedly you saw it. If you took any algebra courses in college, you would have seen it again. You talked about things being solutions. So solution in an algebra sense, or the ways that you saw it used there, was usually something like an ordered pair that was a point on a line or a curve. So it was a solution to that equation. And what it meant is that you were going to actually take that x and that y, you were going to put them in, and you were going to show that it worked, right? That's what it meant usually when they talked about checking to see if a solution worked. And we're going to be doing that as our first steps in this section. We're going to verify the solution. So the word verify here means that it's going to work. So if you find that it doesn't work, you have made an error, okay? It will work. We saw it probably in trig as well when you verified an identity, right? You proved or verified that the left-hand side of some crazy trig stuff equaled the right-hand side of that same stuff, okay? So you've done this sort of thing before, but we're going to do it with calculus now. So the solution that they're giving you that's going to work is y equals e to the negative 2x, and the differential equation is y prime plus 5y equals negative e to the negative 2x. So this is, in fact, a differential equation by the definition we had over here. It involves x, y, y prime, right? I've got x, y, and y prime in this differential equation. You'll see differential equation abbreviated DE all the time. So we're going to abbreviate it that way when we write things down as well. And the solution that it's giving you is that's y equals e to the negative 2x. So to verify that this works, what we're going to do is we're going to take this value for y and we're going to put it in to this y. But notice, we also need to put something into y prime, and we know how to do that. So we're going to take this equation, this solution, and we're going to find what is y prime. So what is the derivative of e to the negative 2x?
Negative 2 e to the negative 2x.
You bet. Is everybody good with that? Okay, so this derivative is going to also, we'll use a different color, be substituted in here. So we're going to take the 3 and rewrite it. We're going to substitute in what y prime is. We just found it's negative 2 e to the negative 2x plus, we have a 5, and we're going to substitute in the y value of the solution it gave us, e to the negative 2x. And we're going to attempt to prove or to show that the result will be negative e to the negative 2x. Now, what you probably remember, or if you don't, you will as soon as I say it, is that when you did this in trig, somebody told you you can't manipulate both sides of the equation, sort of like moving things between them. Do you remember that? The reason you can't do that is because you're assuming that it's equal. And the point is that you're supposed to show that it's equal. So you can't assume something's equal and then like add 5 to both sides. Like that's not okay because you're assuming it's equal to start with. So everything we do on one side has to be self-contained on that side of the equation for whatever side we're working on. On this problem, it's everything we're working on the left-hand side. So we're going to simplify and clean up everything we can on the left-hand side in an attempt to show, and we will, that it's going to equal what's on the right-hand side when we're done. So we're only going to be manipulating on the left-hand side because that's the only side that needs manipulation or cleanup here. So as we work through this, we have negative 6 e to the negative 2x, and then I have 5 e to the negative 2x. So these quantities are the same variable component, right? They match. So here I have negative 6 of them. Here I have positive 5 of them. And so if I combine those, how many of them do I have? Negative 1 or negative e to the negative 2x. And lo and behold, that's exactly what I was supposed to have, right? Okay, so this is actually part of why you've got a written work assignment. Verification inside of WebAssign doesn't work very well, right? WebAssign works pretty well for like finding a solution to something. But we're not finding a solution. We're just trying to show that it is one. And that's why you have written work for this particular lesson. Okay, ready for the next one? Okay, next one. Directions are the same. It says verify the solution. So we're doing the same thing. What's different about this particular one than the last one? It's got a second derivative. So that's really what's different in terms of the operational status of it. The other thing that's different is that the solution is pretty gross. Agreed? I've got natural logs, I've got absolute values, and I've got trig. So I've got a fairly messy solution that we're going to have to work with. But in terms of like what I'm going to do, it's going to look a lot like the last problem, except that I don't need just the first derivative. I'm going to need the second derivative as well. So we're going to find the first derivative, though, first in order to get to the second derivative. Now, looking at this, what do you notice that you're going to have to use to find the derivative of this y value, this expression? Not antiderivatives. You're seeing something that looks like an antiderivative, but we're not going to use antiderivatives. Product rule. This piece and this piece are multiplied, right? So we need a product rule in order to find this derivative of things that look fairly messy. Things are going to clean up in the end on this, but they're going to be messy for a little bit first. So product rule says I'm going to rewrite one of the pieces as is. I'm going to choose the first one, negative cosine of x. And then I need the derivative of the natural log of secant plus tangent. So what happens when I do natural log? It's 1 over. So this will be 1 over. And I only needed the absolute values because I was working with logs. So if you want to remove them at this point, it would be okay. So this is secant x plus tangent x. That's the derivative of the natural log part. But then I need the derivative of the secant x tangent part, right? All the stuff that's inside there. So what is the derivative of secant of x? Secant x tangent x. And what is the derivative of tangent x? Secant squared. Okay, is everybody good with that? That's half of my derivative, but it's the harder half. Okay, right? It's the part that used the product rule for the second piece. The other half of the derivative is that I'm going to take the derivative of the negative cosine of x. So what's the derivative of negative cosine of x?
Sine.
It's actually positive sine of x, right? So this will end up being a positive sine of x at the end. Right, the derivative of negative cosine is positive sine. And then the other part just gets rewritten. So it's the natural log of the absolute value of secant x plus tangent x. So, like, you need to do a little bit of cleanup with trig stuff in calculus. And that's why you worked so hard with it when you were in trig, right? And so we need to clean this up, because what I really need to do is to take another derivative, and I do not want to take another derivative of that. I want to clean it up before I do that, because this would be terrible to take the derivative of as it stands right now. So let's take a look at what's going on here. Notice this secant x plus tangent x and this secant x plus secant tangent x plus secant squared of x is going to have some pieces that are going to clean up, right? I mean, we would expect that they would anyway. And so we're going to try and see if we can get that to clean up. So, Connor, you mentioned that there was an antiderivative something before. What did you notice here?
I was just looking at the natural log secant x plus tangent, but
Okay, I'm going to write that in just for a reference point. What did you notice that was? It's the antiderivative of secant. I think that's what I had written down too, yeah. It's the antiderivative of secant of x. So you never know when those things are going to be perhaps helpful with what we're doing. And so we do want to be a little bit mindful of what's going on with that and sort of jot that down as we notice those things, because they might come into play. Okay, they might not. But when we notice things that are sort of present there, it's a good idea to pay attention to them. All right, so we have, let's see here. I don't have all the details of the cleanup here, so let's see what we have. We have secant x plus tangent x, and we have cosine of x, and this is kind of a mess. I wish I'd written down a little bit more in my notes. So help me out. What are we going to do to clean it up? There is something really nice that cleans up here. What cancels, Braden? What do you notice?
Oh.
Okay, Tanner, do you see something?
Yeah.
The cosine.
Okay,
I was going to say.
not right away. It's not going to right away.
Say factor out a secant.
There you go. Okay, so I'm going to take a step to do that. So this is negative cosine of x. I have 1 over secant x. That is plus, let me move it, plus tangent of x. And then we can factor out a secant here. And if I do factor out a secant, I have tangent x plus, secant of x, like that. The rest of it's going to remain the same. And then this piece cancels with that one, right? That's not the only nice thing that happens. Do you see something else that will nicely clean up over here?
The secant and the cosine.
Cosine and secant are reciprocals. So when you multiply them, you get back 1. So everything here at the beginning that was super terrible and awful is actually -1. Yeah, it's -1. And then we have plus, and we have the sine of x times the natural log of the absolute value of secant x plus tangent x. It does clean up really, really nicely. I mean, like that's a lot of simplification, way better than it was the step before. And now I can actually take a second derivative a lot more comfortably. In particular, the derivative at the beginning, the -1 would just go away. So I'm actually taking the derivative of something that looks a lot like what I started to take the derivative of the last time, right? Last time it started out as negative cosine of x times this quantity. Now I've got sine of x times this quantity. That's very similar. So I'm going to have the first piece written down, and I need the derivative of the second piece. So the derivative of the second piece, I've already done it. It's secant x plus tangent x. And then it's the secant. Can I just write it as the factored version? Are you guys okay with that? It's the factored version that I wrote down. And then plus, and then I need the derivative of sine x. So what's the derivative of sine of x? Cosine of x. And then the second part rewritten, which is the natural log of the absolute value of secant x plus tangent x. So again, this piece is going to clean up very nicely. I don't have the sine and the secant cancel, right? Because they're not reciprocals. But I might be able to change it to something that's a little bit friendlier. Do you know what it changes to? Secant can change into 1 over cosine. So what happens when you multiply sine times 1 over cosine? It's tangent. So this is actually equal to tangent at the beginning. So you have the tangent of x. Again, it's friendlier to write it that way because it's a single trig expression as opposed to being a product or a quotient of something, right? And then I have the other part that's not able to be simplified any. So cosine of x times the natural log of the absolute value of secant of x plus tangent of x. Okay. We just took derivatives. We didn't do what the directions just said yet. I mean, we needed to do everything we did, no doubt. But we didn't actually finish the problem. It feels like we've done enough we should have. We're supposed to be verifying that this differential equation can be solved using the original y solution and the second derivative that we just found, because the derivative itself was not in that differential equation. So I'm going to shrink what I've done and do the last bit. The last bit's actually the easier part of what we've done. So as we're working on the last bit, we're supposed to be verifying this right here. I'll change colors. So I need y double prime. That's what I just took, or what I just found. So tangent of x plus the cosine of x times the natural log of secant x plus tangent of x, okay? And then I have plus the original values that I was given, right? So I was given negative cosine of x times the natural log of the absolute value of secant of x plus tangent of x. And I want to show that this is equal to tangent of x. What do you notice? Yeah. Sophia, can you specify what you mean? So this piece and this piece are identical except for the signs are opposite. So they're going to add to 0. So they're going to cancel. So these two pieces cancel. And I'm left with the tangent x at the beginning, which is exactly what I was attempting to show is equal to tangent x at the end. Okay? So again, the good news about a verify problem is good grief, you know that it has to work at the end, right? And so when we see it work at the end, we're sort of check marking that we found the derivatives and the second derivative's right too, right? And we didn't end up needing to know the antiderivative part that we had seen, but you never know when you might. So it's good to be aware of those things as you're going along. That's what I was trying to, hopefully get at when we're looking at, redoing some of those problems for your exam, is that I want you to have this intuition that's built in that says, I recognize something, I might need that later. All right, let's look at the next one. Okay, again, says to verify, right? So directions are much the same. What's different though? It has some about particular solution and it gives us an ordered pair, right? That's not something we had before. Agreed? Okay, so we're going to verify the first thing. There's two things that we're going to have to verify. We're going to verify that the solution works, and then we're going to have to verify that this point right here also works. Okay, so we'll start with the verifying that the solution works. So if you take a look at the differential equation like we've had before, this differential equation only has y prime, so we only have to take the derivative one time. All right, so what is the derivative of e to the negative cosine of x? Okay, that's correct, Tanner. Tell us what you did to do that.
Derivative of e to the negative cosine is just itself, and then chain rule, the derivative of negative cosine x.
Right. So we've got a chain rule, and the derivative of the exponent is the inside function, and that's going to give you the sine x at the beginning. Very good. All right, so to verify that the differential equation works is to take that differential, or take that derivative, so sine x e to the negative cosine of x, and it's supposed to equal what happens when I put y in, and happens to be the sign on the other side, e to the negative cosine of x, times sine of x. And we don't have to do anything, right? You could shift the sign of the second side to the other, to the front if you want, but these are already the same. Agreed? So I verified it, that's fine. The particular solution part means that that solution itself, that ordered pair, is on the solution that it gave us. So it's sort of a second step of verification. We will take this as an ordered pair and verify that it's in that equation. So we're going to put y in as 1. We're going to put pi over 2 in for x. So y equals e to the negative cosine of x. Y is 1, and the x value is pi halves. And we're going to verify, again, now that a specific ordered pair, this is like a college algebra kind of thing at this point, that it actually works. So if I put in pi over 2, what is the cosine of pi over 2? It's 0. So I'm only going to manipulate the right-hand side because the left-hand side's 1. It doesn't get any simpler than that. So this is e to the technically negative 0, but negative 0 is the same as 0. What is e to the 0?
1.
Yeah, it's 1. And you're done. Okay, so it's just a second layer of verification. You're verifying that the point that they gave you is really on the solution that they gave you as well. Okay, easy enough? All right. What's different about these directions? We're going to learn to read directions really well in this section.
We're not verifying.
It does not say verify. What does it say? Determine. What's the difference in those words?
Might not be right.
It might not work. That's exactly right. Verify means you know it's going to work. So at the end, when it works, you're not surprised. You're check marking and you're done. Right? So if it doesn't work, you know you made an error. If it says determine, it means it might not work. So we're going to figure out if what they're giving us works, and the answer might be yes and the answer might be no. Right? So we could have either of those things happening. Have you seen this notation before? Our calc book doesn't, oops, I meant to highlight that. Our calc book doesn't really use this notation much, but you might have seen it in some other version if you've taken calculus anywhere else. Has anybody seen that before? Okay. So it looks like it's basically y to the power 4, but obviously that must not be what it means, or there wouldn't be parentheses there. Agreed? Those parentheses must mean something. So when you see something that looks like a power but it's in parentheses, it actually means it's a derivative, and it's the fourth derivative. Okay? So generally speaking, if y is, you take the derivative, we put y prime. We do the second derivative, we do y double prime. If you do the third derivative, you might actually see y triple prime listed, but if it gets any bigger than 3, it will divert to this. So if you wanted the 50th derivative, it would have y and it would have a 50 in the parentheses. We're not going to take a 50th derivative, Sophia, I promise. But that's what it would look like. Okay, so the parts that are in parentheses actually mean we're taking a derivative that many times. So in order to verify that this particular solution does or doesn't work for this differential equation, which is y to the power, or to the fourth derivative of y minus 16y, we need to find the fourth derivative. And this is not a terrible one to take the fourth derivative of. It's not like the last one we did. So if we do the derivative here, what is the derivative of 2 sine x? 2 cosine x. You guys can just spit this one out pretty quick. What about the second derivative? Negative 2 sine of x. I'll write the third derivative with 3 primes, and then I'll switch to other notation. So what's the third derivative here? Negative 2 cosine of x. And then the fourth derivative, notice that new notation with the 4 in parentheses. It's 2 sine x, and notice you're right back where you started, right? There's a cyclic pattern when you're dealing with sines and cosines. So they're actually very friendly. That's why we see them used a lot with integration by parts. That's one of those red flag things. Integration by parts often, not always, but often has sines and cosines in them. And so because they have this cyclic pattern to them. All right, so we have the fourth derivative now. And so I'm supposed to be putting that into here. So this is y, I'm sorry, not y, 2 sine of x. And then it says minus 16. And then I want the original y that I was given, which is 2 sine of x, happens to be, equals 0. So this is 2 sine x minus 32 sine x. And what do you get when you combine those? Negative 30 sine x. And more pointedly, you don't get 0. Now, are there x values that make this equation true? Yes, there definitely are, but that's not what we're trying to show. We're trying to show an identity, right? That it's perfectly identical on the left and on the right, and it simply isn't. So this one is not going to be, let me do it this way. So y equals 2 sine x is not a solution to this differential equation because it won't work. And I'm going to introduce some notation you may not have seen before. You may have, depending on your math background. Do you know how to write for all?
Is it like the upside down triangle with a line?
Kind of. Yeah, so that's a decent way to describe it. It's an upside down A. This is for all. It does not work for all x. Yeah, we'll use more of that as you get into other math classes. You'll see more notation. So I'm going to try and start using some notation at different points when it comes up. This is one of those places where it's nice. It doesn't work for all x. It does work for some x, but it has to work for all x for it to actually be a solution. Now, that doesn't really help you if you really wanted to know it was a solution and you just found out the answer is not. Like, it just doesn't work, right? So just in life, you try things sometimes and they don't work, and it narrows down the possibility, but sometimes that's not always what you really wanted. You wanted it to work so you have a solution, right? So we do need to figure out at some point here how we find solutions, and we're getting close. In fact, we're there, right? Direction's changed, and it says we're going to do what? Find a particular solution. So we're no longer verifying that it does work. We're no longer determining does or doesn't it work. We're actually going to find a solution this time. Now, it's kind of, we're easing into it. It says find a particular solution. They do give us a general solution. So the fact that they gave us a general solution means that it really is going to work, but it's working in general, and we want to find the very specific one that works instead of it being in general. So notice they're calling this a general solution in particular because there's some dummy variables in there, right? Like there's a C1 and a C2. And we're going to actually figure out what is the C1 and the C2 that make this work. Okay, so this happened in Calc 1 when you were finding general antiderivatives, and then we found particular antiderivatives. Do y'all remember that? So when you find general antiderivatives, you always put plus C on the end, correct? And then when you find particular antiderivatives, it means that they have to give you an ordered pair for you to figure out what the C is. This is along those lines. So it doesn't actually ask us to verify that this works. We're told that it does, so we kind of get to skip that step. It's not necessary for this particular problem. We're not verifying anything. It's going to work. But we do have to find what the C1 and the C2 value are that make that happen. So if you take a look at this, it says our differential equation is y prime minus 2x equals 0. But the reality is that since we know our solution works for that differential equation, we don't care about that differential equation in this particular problem. We just need to figure out what in the world we need to let our C value be in order to make that work. Okay? So let's take a look what this happens. So we're going to take this ordered pair, just like in Calc 1, and we're going to plug it in. I've got an X value and I've got a Y value, and the only thing I don't know is C, so I should be able to figure out what C is, right? Just a basic substitution problem from an algebra class. So we put in the X value as 0. We put in our Y value as 3. And what does our C value end up being from that? It's negative 9. So our particular solution is 2x squared minus y squared equals negative 9. That's it. Okay, that's it. I told you we're easing into it, right? We're just finding the C value that we would need for a general solution given to find the particular solution.
So in this case, we didn't need the...
Differential equation. Correct. We didn't need the differential equation. We will in the next one. Okay, so we're building slowly. So in the next one, it asks us to verify the general solution. We didn't have to do that last time. Now we are. And then we're finding the particular solution. Okay, so we're doing both components now. So we are going to need the differential equation on this one. Notice the differential equation does have a y double prime. Agree? So we need to find y prime, and we'll need to find y double prime. So and you can do this in either order. I'm going to do it in the order that was sort of asked of me. Oh my goodness, and now it's gone. I don't think I can undo it either. Oh, I can. There's a tool palette that I pull down and accidentally when my hands get in the wrong spot, and it can delete slides completely, and they can't be coming back sometimes, or at least I don't know how to. But we got it back, so that's good. All right, so we're going to find the derivative of this expression. It says verify, that's sort of like we're going to do part A, and then it says find the particular solution, that's sort of like part B. So we're doing two steps. This is kind of combining what we did at the very beginning, the verification, with what we did on the very last problem, finding the particular solution and figuring out what this, in this case, C1 and C2 are. All right, so we need to find the derivative. So what is the derivative of this y equation? Well, the derivative of C1 is 0, because it's just a constant, right? What's the derivative of the C2 ln x? C2 over x. Or, because we're going to need it in a moment, I'm going to rewrite this as C2x to the negative 1. Okay, everybody good with that? Constant C2 comes along for the ride because it's a constant multiplier. The C1 is a constant that's added, so its derivative is 0. Now we're going to do the second derivative. So what's the derivative of C2x to the negative 1? Yep, and I'm going to rewrite it back in that fractional form too, if you prefer to see it written that way, especially because we're going to start evaluating some things. It's a little bit nicer. Okay, is everybody good with those two derivatives? Okay, so we're going to verify that it actually works for our differential equation. Our differential equation says to take x times y double prime. Well, that's the negative C2 over x squared. And we're supposed to add that to y prime. So y prime was C2 over x. Was it negative as well? Nope, it's positive. And we want to verify that this is equal to 0. So what happens on the first piece? Yep, one of those x's from the denominator is going to cancel with the x over here. That's going to leave me with negative C2 over x plus C2 over x. And sure enough, you add those together and you get 0, right? So we verified it. It worked. Now we're going to figure out what C2 and C1 are. Because they ask us to find two variables, not two variables, but two constants, C1 and C2, they have to give us two pieces of information in order for that to happen. Right? On the last problem, we were only finding C. So we only needed one ordered pair for that to happen, one piece of information in particular. Here we need two pieces of information, or I'm not going to be able to find both C1 and C2. I'd only be able to find one of them. Now, it looks a little bit funny. Sorry, where did all my stuff go?
I think they're just ahead, so.
I don't think so. It disappeared. I told you things were going to disappear. Okay, I'm going to copy this to the last slide. And I'm going to write in the pieces that are missing. It's on your paper, hopefully, as well. The part where we're on tells us that y equals 0 and y prime equals 1/2 when x equals to 2. I didn't even see it happen. That was crazy. All right. So those are the two pieces of information. It kind of looks like there's three pieces, but what they're actually telling you is what y is when x is this value and what y prime is when x is this value. So there's kind of two sets of ordered pairs there. One's relating to the original equation and one's related to the derivative equation. So let's actually start with the derivative equation because the derivative equation only has one variable in it, C2. So if you take a look at the derivative equation, let me move that back down over here. Okay. There. If you take a look at the derivative equation right here, we can use the information for y prime is 1/2 when x is 2, and we can figure out what C2 is because that's the only piece that's not known in that equation. So over here, I can do y prime equals C2 over x. Y prime is supposed to equal 1/2 when x is equal to 2. So what does that tell us about C2? C2 is 1. Yeah? Okay, so that's one of them. We've found one of them now. So now my original equation, which is not on this screen, but it was y equals C1 plus C2 ln x, is now y equals C1 plus ln x, because I already found that C2 is 1. And now I can use the other piece of information. So the other piece of information says that y is equal to 0 when x is equal to 2, like this. So it may not look like a very nice value, but I do have a value for C2. What is it? Negative natural log of 2. So my solution, right, my general solution right here, actually I'll take the one that I had sort of partially already done here, is now y equals negative natural log of 2 plus the natural log of x. And I'm fine with you leaving it like that. There is another way this could be written. How else could you write this?
Natural log of x over 2.
Yeah, natural log of x over 2. I don't care that you do that, but I just want you to know there is another version of that that's pretty nice. Okay, so two pieces of information in order to get to there. Okay. You ready to look at 6? Let's see if the 6 is still here. Yep, it is. Well, that's not supposed to be here, but the rest is there. Okay, number 6. What's number 6 say? It says integration. It also says we're going to find what kind of solution? A general solution. We didn't have to find the general solution in the last two. They gave us the general solution, and then we either verified or didn't. And then we found the particular solution. So now we're actually going to find the general solution. So again, we're adding a layer on one at a time as we work through 6.1. Now, this is going to come into play. So I don't know if y'all remember back in Calc 1, but when you first learned integration, in my class, I know I talked about putting the script s at the beginning and the dx at the end. And I told you the reason there's a dx at the end is because it specifies which variable you're working with. Do y'all remember that? Sound vaguely familiar? Okay, so you're going to see it come into play for the first time here, why that mattered and what we're going to be doing. So the first thing that we're going to do as we're using integration to find this general antiderivative is that I want the dy's, or I want the y's actually, everything with y needs to be on one side and everything with x needs to be on the other side. I'm going to separate my variables, okay? Now, you can't separate variables always in differential equations. Like there are going to be ones you're going to encounter along the way, but that's for another course. Yeah. We're going to be working with ones for the most part, especially in these first couple of sections where we can separate them. Okay, so the first thing I'm going to do is I'm going to move the dx to the other side. So it's going to look like, and in some sense you can think of it as a multiplication problem. So I'm separating this to say dy equals x cosine of x squared dx. I multiplied dx to the other side. Everybody good with that? Okay, dy dx means derivative, but it's also a ratio, right? It's a rate of change. It's a description of how y is changing with respect to x. So I've separated it so that I have y's on everything on the left, x is everything on the right, and now I can drop in those script s's, right? Those antiderivative notations. So on the left, I'm taking the antiderivative with respect to y, and on the right, I'm taking the antiderivative with respect to x. Now, this is always a gateway question that shows up for me because I want you to know that when there's nothing there, it's an understood one. What is the antiderivative of 1 if you're taking the antiderivative with respect to y? It's y. So I get y on the left. Now, technically, I get y plus c, but I need to put a plus c either on the left and on the right. I don't really need to put it on both sides because I could consolidate it and shift it if I needed to. So I'm just going to wait and put it on the right hand side, with the x. Okay. Here's something else that's really cool about this section. Are you ready? What chapter are we in?
6.1.
Okay, we're in chapter 6. We're in section 6.1. We're in chapter 6. Chapter 6 follows chapter 5. So everything that you learned in chapter 8 is not going to be here. Levi's very excited. So think about for a minute. What tools did you have in chapter 5 when you were finding antiderivatives? U substitution, algebra manipulation, trig manipulation. That's it. There's nothing else. So you don't have to look at this and say, is this integration by parts? It's not going to be, right? This is a U substitution problem. What's my U? What is it?
X squared.
X squared. Okay, good. So my U is x squared, which means my du is 2x dx. The x and the dx are there. The 2 is not, so I need to divide the 2 to the other side. So I'm going to have a 1/2 here. The x at the beginning, the dx at the end are going to get absorbed into a du. And then my x squared will become u. All right, what is the antiderivative of cosine of u? Good, negative sine of u. And then plus c, right? And then we are going to put into this the x squared that u is equal to. And we have found our first general antiderivative. Right? Everything else has been given to us along the way. This is the first one we've found ourselves. Okay. Ready to try another one? It's going to work a little bit differently. The first part's going to work the same, right? What do I have to do first? Got to multiply the dx to the other side. So I'm going to move that over. So this is dy is equal to 5 e to the negative x over 2 dx. Now what? Integration. So we're going to put the script s on both sides. What's the antiderivative of dy? Y. All right, what about the right-hand side? What do you see? U substitution, right? Okay, what's u going to be for this one? Negative x over 2. What is the derivative of negative x over 2? Negative 1/2 du. I'm sorry, dx. Get the right there. There. I don't have a negative 1/2. I have a 5, but I don't have a negative 1/2, so I'm going to have to multiply that to the other side as negative 2. So I'm going to incorporate the negative 2 here with the 5 here. That's going to give me negative 10, and I'm going to put it in front of my integral. And then this is e to the u du. Okay, is everybody okay with my substitution step? I kind of merged a few things together. Okay. What's the antiderivative of e to the u?
U.
Yeah, e to the u. And then plus c, right? And then my u is negative x over 2. All right, everybody good? Okay.
On the written work, are you
Yeah.
going to want us to show like the
So, do you, okay, by the first step, do you mean,
Like taking the integral of dy, yeah.
so you need to show that you're dropping the integrals in there somewhere. So you're going to have to show me that. If you didn't show me that you moved the dx, would I be like okay with that? I'd be okay with it. I don't like it very much, but I'd be okay with it. The other thing too, this is where I thought your question was going to be, is do I actually need to show the u substitution? When there's a simple linear u substitution, if you can process through that without showing it, I'm okay with that. Most of the ones that you really need to show are the ones that look more like there's a like something more than just a linear substitution, and so those you probably should show. But if you can avoid showing the u substitution here and still manage to get to the -10, okay, that's all right with me too.